Okay guys, the next thing I want to look at is allosteric ligands. Everybody see that in your notes? It says there in the first line, they bind to a site away from the active site. That's a key thing to know. That's what's been asked over and over on old tests. The other one that they seem to ask is wanting you to know that ATP is an example of an allosteric ligand. So make that clear in your notes. ATP is an example. That's the two things they've stressed over and over on that. Okay guys, let's look at reaction rates next. And I want to show you this visual to kind of give you a break from looking at the notes for a minute. If they ask you which of the following can increase reaction rates, the key things you want to pay attention to is an increase in temperature, an increase in substrate concentration, an increase in enzyme concentration, and a decrease in inhibitor concentration will do that, okay? So in your notes, you can just make a comment on that, put up arrows and down arrows to make that really clear to you, but all that's pretty common sense. As you turn the page, you're going to see a box that talks about ATP. What do we say ATP is? An example of an allosteric inhibitor. Good, okay? And if you read on that box, it says ATP is unique because it can be a substrate and an allosteric inhibitor. So pay attention to that. These aren't super high yield points. They've been asked occasionally, not every time, but that's just kind of an all-star thing to know. The rest of this stuff I would kind of pause and skim. It's not a high yield page. Just kind of pause and skim and get the main points. Okay guys, now we're going to look at Gibbs free energy. And I want you to take a look at this visual here on the screen with me for a second, okay? Now, if they ask you a detailed question on this, the likely scenario is that they want you to understand what's going to lead to a negative change of G, okay? That means that energy is going to be given off in the reaction, okay? So when energy is given off in a reaction, that's when it's most likely for the reaction to proceed, okay? So look at this logically and ask yourself, what's going to give you a negative change of G? Well, if you just do basic math on this, you're going to see that a negative change of H, right, is going to be more likely to lead to that, and that's enthalpy, okay? So they might even ask you, is it going to be a positive change of H or negative change of H? Make sure it's negative change of H. That's enthalpy, right? That means heat's given off. The other thing I would pay attention to is the change of S. Do you guys know what that is? That's going to be entropy, yes. So you want a high degree of entropy, which is another way of asking about randomness, which is, by the way, something they asked on old tests. So pay attention to that. If they ask which of the following thermodynamic parameters is a measure of randomness, that's going to be that, okay? It's going to be entropy. So pay attention to that. So you want high entropy. You want a lot of these balls running around all over the place in the reaction, right? You want heat to be given off. And the bottom line is you want a negative change of G, all right? That's Gibbs free energy. Okay guys, let's talk about oxidation reduction reactions just for a little bit. If you look in the box with me right now, you'll see that it says, remember Leo the lion says grr, right? So you got to have some dorky stuff like that in biochem to make everybody not want to slit their wrist, right? So if you look at lose electrons oxidized, right? It says gain electrons reduced. Bottom line is, I want to look at the bottom of the page with you with FADH and NADH. It says they're both electron carriers, okay? So the way you need to think of electron carriers is that they carry electrons like this, and then whatever they give their electrons to, it reduces whatever they give it to, right? So the point you want to know right now is look at this visual with me for a second, okay? You need to put NADH and FADH on the same team, okay? They're going to give their electrons to make ATP, okay? And you're going to see that in the Krebs cycle. Whereas NADPH is going to donate its electrons, right? Every time you donate electrons, you energize a process, right? So when NADPH gives off its electron, the whole purpose is to make molecules, right? So you can see that on here. And by the way, whenever you see NADPH on the exam, immediately think pentose phosphate shunt. That's where NADPH comes from, as a pentose phosphate shunt. Remember, if they ask you NADPH is an electron carrier, it's going to give off its electrons for the purpose of making molecules, right? Like fatty acids, you're going to see that later on in your notes. So have that distinction in your mind. NADH and FADH are on one team to make ATP, NADPH on the other team in order to reduce to make molecules. That's the key thing you want to focus in on that point. Okay guys, now we're going to talk about buffers and pH. And there's been a lot of predictability on past tests on what they've hit on this, which is awesome, because some of this can get pretty complex or it can be very basic. They've chosen to be pretty basic. So look at the notes with me for a second. If you look at the first sentence there, it says, the formal definition in bold is pH equals a negative log of H plus concentration. So look at this visual with me for a second, because you need to know that definition, but you also need to remember pH plus POH is going to equal 14. Okay, so they could easily give you something like this, where the H plus concentration is 10 to the minus fifth molar concentration. They could give you something like that. So as soon as you see that, you would know the pH is going to equal 5, right? If the pH is 5, that means the pOH, which is what they asked on this question, is going to be 9. Okay, so just take a look at that, remind yourself, it's basic stuff we've had for years, but remind yourself of those two equations so that when you get this on the test, you'll be ready to dominate it. Okay guys, let's talk about buffers for a minute. And just to introduce this topic, just remember that cells all throughout your body are constantly undergoing reactions in which they release H plus ions. Sometimes they release them outside of the cell, sometimes the H plus ions are inside the cell. So take a look at this visual with me for a second to introduce this topic. So when you think about releasing hydrogen ions, sometimes they're going to be in the cell, and on some past tests they've asked what is the buffer in that situation, and it's going to be dihydrogen phosphate. Okay. In other cases, they've asked what's going to be the main buffer when H plus ions are released outside the cell. Okay, and that's going to be carbonic acid. All right. So if you look right now, guys, at the bullet points in your notes, it's mentioned right there for you. I just want to give you some context on how to think about that. Both of those have been asked on old tests. So take a look at that and remember H plus ions. It's going to differ the question based on whether it's in the cell or outside of the cell. Okay guys, you might also remember that proteins are awesome buffers, okay? And if they ask you on boards, why are proteins such a good buffers? Which, by the way, they've asked this multiple times. Go in your notes where it says the capacity of the buffer in bold, okay? Look at the paragraph above that. It says that proteins are capable of buffering solutions over a wide range of pH. Why? Because they contain many different functional groups with different pKa values. That sentence verbatim has been on old tests, so pay attention to that, and that's understanding again why proteins make for good buffers. Now, if you want to elaborate on that more, you can go to the Henderson-Hasselbalch equation, okay? And if you look right there in the box, that's the key statement that's been asked as well. It states that the pH equals the pKa when an acid is half neutralized. Okay, that statement verbatim has been on there. You can look at the equation and play around with that a little bit, but that's the statement that they've been hitting hard in past tests, so pay attention to that. Okay guys, the next big heading we want to look at is protein metabolism. This is going to be an easy one and a short one. I would just know these two terms mean that you're breaking down a protein, okay? And the whole idea is to break down the protein and get ATP out of it. So as you look at this here, transamination and oxidative deamination. If you see either one of those terms, okay, especially transamination, pay attention to that. That's the breakdown of proteins, okay, to get ATP. So that's something I would hone in on. You can see, if you want to read more about it, you can. It hasn't been a hot topic, but that's something I would just kind of make a mental note of for the test. All right, guys, if you look in your notes, you're going to see a box that talks about nitrogen balance. And when you see this, you want to immediately think amino acids. Remember how amino acids have NH2 in them, right? We said nothing else has that in terms of lipids or carbs. So if they ask you any question on the test about nitrogen excess or deficiency, you want to think about amino acids. It's right there in the box. Pay attention to that. It's been hit over and over and over again. Okay guys, the next heading we want to look at is bacterial metabolism. And there's a sentence here that's huge, okay? Go down to the Embden-Meyerhof pathway. Read that with me. It says the most common type of bacterial glycolysis is going to be anaerobic and facultative anaerobic bacteria. That word anaerobic is huge because when you circle that, you want to write right below it lactic acid, okay? Because as you see here on the past test question, take a look at this with me. The key thing they want you to understand there is understanding that, first of all, it's going to be anaerobic, so you're going to get lactic acid, right? And lactic acid is karyogenic. That's the other key point they want you to know that's been mentioned multiple times on old tests, and it's right there in the bullet point here in your text for you, okay, to know that it is karyogenic. So say that to yourself. Bacterial glycolysis is going to be anaerobic. It's going to produce lactic acid. Lactic acid is karyogenic. That's the key thing they've stressed on old tests, so hone in on that as you're studying. The next thing we want to hit, guys, is carbohydrates, right? So we're on to a totally new portion of the outline here in this section. And you can see right away carbohydrates, if you look at the structure, let's look at the notes together, there's no nitrogen in there, right? And you can break carbs into monosaccharides, disaccharides, and polysaccharides, right? If you look at monosaccharides, the first thing I want to point out to you guys is that they're absorbed by enterocytes in the small intestine, okay? And that has been mentioned before in the past, so you want to think enterocytes in the small intestine. So when you're breaking down a carb, you got to break it down to the smallest individual unit before it can get absorbed, and that's the monosaccharide. Now, if you go to disaccharides, I don't know how you guys want to memorize this, but I always think of it like I'm a die-hard, like disaccharide. I'm a die-hard MLS fan, like Major League Soccer fan, right? So whatever you want to use with MLS, just remember the disaccharides all start with M, L, and S. And I know that's super basic and you could be like, geez, thanks for wasting 30 seconds of my time. But you need to know that because if you know MLS, which is maltose, lactose, and sucrose right here in your notes, they have asked a lot of questions on this because they want you to know each one of those of the MLS is glucose plus something else. So for example, maltose is glucose plus glucose. Lactose is going to be glucose plus galactose. So whenever I say lactose, I always think lactose like you lack something. So I think of it like you lack a gal in your life, like you're single or something. So when I think of this one, I think lactose, I think galactose. Okay, that's got to go together in your mind. Last but not least is sucrose. This one's easy too because you want to think su and fru, like sucrose, fructose, okay? Combine those in your mind. So let me show you an example of how this was asked on a past test. Okay guys, now let's look at starch together. It says right there, starch is composed of thousands of glucose subunits. It's a storage form of glucose in plants. And if they want to get really, really picky, this is the way they've shown this on past tests. So take a look at this. Now you might be thinking, how in the world am I going to remember amylose and amylopectin? Well, think of Amy at the beginning of the word, okay? Amylose, amylopectin. Think of Amy as a star if you want. So if they ask you anything about starch, a really picky question, it's going to be a combination of two Amy's. Think of it that way. If you get into glycogen next, everybody, the first thing I want to point out about glycogen, that's a storage form of glucose, and you want to remember liver when you think glycogen, okay? Think liver. That's going to be the main place that this is formed. I'll talk about that in a few pages. Now the next thing is glycosaminoglycans. These are GAGs. You guys know these are repeating disaccharides. Now as you look in your notes there, if you read that paragraph, it says they have high viscosity and low compressibility, okay? So, one of the things that they've asked 2 different times on GAGs is this. So take a look at this on the screen. So as you look at that question, the big take-home message is that you see on this page all the different types of GAGs, right? And so I wouldn't necessarily dig into each one like at a ton of detail, except I would know chondroitin sulfate is the most common GAG. But as you look at these, the reality is they just want you to know which ones are GAGs. Now they could obviously choose to get pickier than that, but that's really the degree of how much I would look at it. I would pause the video, skim through them quickly, and move on with your life. The next key point I want to focus on is proteoglycans. You guys probably remember that proteoglycans are negatively charged, they attract water, but this is a really picky question they've asked in the past on wanting to make sure you really understand why they're able to attract water. So check this out. Okay guys, when we were talking about digestion of carbohydrates earlier, do you remember how far you have to break a carbohydrate down in order to get it absorbed? All the way down to a monosaccharide, yes. So look in the box here, it says, during digestion, O-glycosidic bonds, okay, which by the way, those are the bonds that link polysaccharides. If you read on it, says these are hydrolyzed, so they're broken down to produce monosaccharides, which by the way, where are monosaccharides absorbed again? Yes, in the small intestine by what? By enterocytes, okay? Yes, so that's been again stressed several times, so make sure you pay attention to that. Now, if you look underneath bacterial polysaccharides, one of the ones I want you to focus in on is where it says dextran. Right below that, it says sucrose is degraded into what? So remind yourself, is sucrose, is that a disaccharide or monosaccharide, everybody? Sucrose is a disaccharide, right? Because you're a diehard MLS fan. So what's sucrose again? It's always glucose plus something, right? So sucrose is glucose plus fructose, yes. So again, they've asked that in multiple different ways. It's an easy thing to look out for on the test. Okay guys, now we're going to talk about saliva for a little bit. And I created this visual for you to kind of summarize the key points. So take a look at this as I summarize this for you. Number one, you want to know that saliva obviously initiates digestion. And if they ask you, how does it initiate digestion for starch? If you don't know much about starch, you're always going to say Amy, right? Amylase, yes. If they ask you about how does it do that, right? For lipids, you're going to say lipase. If they want to know the main buffer found in saliva, you're going to pick bicarbonate. If they want to know the main antibody found in the saliva, you're going to say IgA. If they ask you what's the number one gland that produces saliva, you're going to say the submandibular gland. Yes. And if they ask you the number one risk factor for caries activity, you're going to say pH less than 5.5. Yes, and you're also going to say the frequency of sugar contact to the teeth, right? So those are the key factors you want to pay attention to. You can go ahead and pause and make sure you got the other key points, but those are the main ones that I would pay attention to as you're studying. Okay guys, we're going to talk about glycolysis now. You guys might remember glycolysis happens in the cytoplasm. You know that the big picture with glycolysis is to take glucose and get ATP. Yes, okay, that's the idea. And I want to show this to you on a visual to kind of help you soak up the big picture concepts. First of all, glucose is going to be converted to pyruvate, right, at the end of glycolysis. If there's oxygen present, pyruvate is going to be converted to acetyl-CoA, and that's going to enter into the Krebs cycle, okay? If there's not oxygen present, then pyruvate is going to get converted to lactic acid, and that's going to be transported to the liver, okay? So I want to show you this on a visual here for a second, okay? And I want to make sure this is something that you can see visually because I think it's way easier than trying to memorize everything, okay? So as you look at this visual with me, the first thing I want to point out is everything at this spot right here in the diagram, that's all going to be in the bloodstream, okay? This right here is a cell membrane. So this area right here is going to be the cytoplasm. This right here is the mitochondria, okay? You got kind of your bearings straight now as we look at this? Good. So let's start with glucose here. Glucose can be converted into glucose 6-phosphate, okay? And when it does that, gets converted to glucose 6-phosphate, now that is like a magical moment because glucose 6-phosphate is really, really important. They like to ask a lot of questions about it because glucose 6-phosphate, that's the first step of glycolysis. It's going to end up being converted to pyruvate, right? Or glucose 6-phosphate can be pulled back into the blood and be made into glycogen, okay? So that's a key concept you're going to see with glycogen is it's all about glucose 6-phosphate. And we'll talk about that again in your notes in a minute. Okay, the other thing I want to point out is as you get up here to pyruvate, again, if there's no oxygen present, you go to lactate, go back to the liver in this direction just like that. It's a big deal. If there is oxygen present, pyruvate is going to get converted into acetyl-CoA. But for it to transport right here in your diagram across into the mitochondria, it needs what's called the pyruvate dehydrogenase complex. Now hang with me, don't fall asleep. Because on old test, they pointed out that coenzyme A, which is part of that complex, right, is essential for that transfer. Now if they want to get really picky, and they haven't done this much on old test, they want you to know the 3 coenzymes that make up the pyruvate dehydrogenase complex. And that is coenzyme A, NAD, and thiamine. Okay, that's what's going to allow the ability to move pyruvate into the intermitochondrial matrix. And you guys know once acetyl-CoA gets in there, there needs to be a reaction, okay? And that reaction is going to be what's going to convert acetyl-CoA, right, into citrate. Okay, so actually that first step is taking oxaloacetate, converting it to citrate, and that enzyme is citrate synthase, okay? And that's what allows that first step, which is to get the Krebs cycle going, all right? Now, bottom line is, when you think about the different scenarios, acetyl-CoA is a really, really big deal. So let's pull that out here and take a look at that. Because on the test, they like to ask detailed questions about acetyl-CoA. Number one, the first thing acetyl-CoA can do is to enter the Krebs cycle. Yes, and again, what enzyme do you need? Citrate synthase. Yes, citrate synthase. Number two, if you don't have that enzyme, no citrate synthase, then you're going to produce ketone bodies, and they love to ask this, okay? So make sure you memorize that enzyme citrate synthase. Number three, it can be converted to malonyl-CoA. And when you look at that, first thing you want to pause on, if you haven't heard of that in a long time, you want to think fatty acids, okay? Because over and over on tests, they've asked that concept of acetyl-CoA getting converted to malonyl-CoA is how you make a fatty acid. And later on in the notes, you're going to see when you break down a fatty acid, guess what? You break it from a fatty acid down to malonyl-CoA, which gets broken down into acetyl-CoA. And last but not least, acetyl-CoA can be converted into cholesterol. It forms the core of cholesterol, okay? So that's kind of the key concepts you want to get about acetyl-CoA. You're going to see this in your notes in a little bit, but I love this diagram because it kind of helps you see the big picture. And last but not least, I want to show you point number one, which is entering Krebs cycle. If it does enter the Krebs cycle, right, it's going to spin around, it's going to create this proton gradient across the electron transport chain right here to create ATP. And that's the big point by the way, of glycolysis is to create ATP through this process. One other thing I want to point out, when you guys think about lactate up here for a minute, we talked about how if there's no oxygen present, lactate can be taken to the liver, right? And as it's done that, as it's being transported across and into the liver, remember, I'm going to show you this in a second, there's a process called gluconeogenesis in which you make new glucose. Do you guys remember gluconeogenesis? Yes, okay. They might ask you on boards, what are the 3 things that can be used for gluconeogenesis? And I always remember the mnemonic LAG, L-A-G. You're going to see that in a minute. Okay, but lactate is the L. So bottom line is, let's say you don't have oxygen present, right? You make lactate, right? Lactate can go to the liver down here and can be converted into glucose, and you can go through the whole process again of glucose to glucose 6-phosphate, and you can try again. So if they ask you on boards, lactate is the L, amino acids, right? And glycerol. Those are going to be your lag that make up gluconeogenesis, okay? So this diagram, I'd encourage you to kind of watch this again, make sure you have it really down in your mind. And to reinforce this structure, I'm going to go through the next few pages to make sure you got it. Okay guys, we're going to talk about the pentose phosphate shunt. You guys might remember me saying earlier that the whole purpose of this is to produce NADPH. Does that ring a bell? Yes, and we said NADPH is going to take these electrons and use it to donate it to processes, right, to create molecules like fatty acids, steroids, etc. Okay? As you can see here in the notes, it says the pentose phosphate shunt metabolizes glucose 6-phosphate. So that should be like a happy place in your mind where you want to go to your notes and find that. Remember in the diagram we just talked about, and we obviously talked about it and being used to go forward in the diagram and go into form pyruvate and Krebs cycle and all that. We also said it could be taken back into the bloodstream, right, to make glycogen, which we'll talk about again in a second. The other thing glucose 6-phosphate can do is be shunted, aka pentose phosphate shunt, into a process to produce NADPH right here, okay? So right there it says NADPH is used in the synthesis of fatty acids, steroids, also to produce ribose 5-phosphate, okay? So those are key things you want to pay attention to. The next word we want to look at is gluconeogenesis, okay? If you spell that out, it obviously means you're making new glucose. Now, the key thing I would point out in your margin is that you're making new glucose to put into the bloodstream, okay? Not into cells. So when you think of it that way, to put into the bloodstream, you want to understand if they ask you on boards, does insulin want this or glucagon? Now, hang with me for a second, all right? Actually, let's just look at this together. Let's look at this visual. We're going to see insulin is all about storing things, all about putting glucose into cells, right? So when you think of insulin, think parasympathetic system, they're on the same team. When you think about glucagon, you want to think the purpose of glucagon is to put glucose into the bloodstream, okay? So sympathetic nervous system is going to be on the same team as glucagon. So when you think about gluconeogenesis, putting new glucose into the bloodstream, obviously glucagon is going to be on the same team as this. And on past tests, that's a typical kind of standardized test question, is to want you to understand how all of this fits together in the big picture. Now, some really good stuff I love about gluconeogenesis is that they want you to know what 3 substances can do it. And we already talked about lactate, amino acids, and glycerol. So think of it like you're lagging, you need some more glucose. These 3 things can do it. Now make sure that you don't put acetyl-CoA on boards. Make a note in your margins that A is amino acids, it's not acetyl-CoA. Because acetyl-CoA can do a lot of different things. We talked about 4 things just a few minutes ago that acetyl-CoA can do, right? But it cannot be used to make new glucose. That's really important and something I would pay attention to. So I want to show you this kind of schematic too, as we've just talked about insulin and glucagon. I want to ask you the question, what about glycogenolysis? If they ask you that, remember glycogeno, you're making, right? Glycogenolysis. Think about glycogenolysis as being you're breaking down glycogen, right? The whole reason why you're doing that is to put it in the bloodstream. So the person that's going to want that, again, is going to be sympathetic nervous system or glucagon, okay? If they ask you about glycogenesis, you're making new glycogen, right? Who's going to want that? Well, glycogen is obviously the stored form of glucose, so the parasympathetic system is going to want that. So I just kind of wanted to show you a few of those terms and how they can get a little pickier on boards about how they break that down. Now guys, the next thing I want to show you is the lactic acid or the Cori cycle, okay? First thing I want to point out, it's all about lactic acid. So if they use Cori cycle, make sure you know it's going to be a question about lactic acid. And the whole idea is if you're working out and you have all this excessive lactic acid, how can we get rid of that? How can we use that in a positive way? So it says here in the second bullet point that excess lactate can diffuse into the blood, travel to the liver, and then it goes on to say it can be the liver then can convert lactate to glucose through what? Gluconeogenesis. So we just talked about that, right? So the whole idea is that lactate is always going to the liver. That's the key thing you want to remember. Once it's at the liver, you can take that glucose, you can convert it into glucose 6-phosphate and go down that process again, okay? So you guys know lactic acid accumulation can cause cramps. So the whole idea is we need to clear out this lactic acid. The Cori cycle helps with that. So the next heading is glycogenesis. You guys know this is making new glycogen. If they ask you on boards, you want to know this is going to happen in the liver. If they ask you any question about glucose regulation, always pick liver. That's going to always be your top option. Okay guys, now we're going to talk about glycogenesis. And what I want to do is put that visual back up there again for you so you can see that, all right? So glycogenesis, as it says here in your book, involves the conversion of glucose into glucose 6-phosphate and then into glucose 1-phosphate and then into UDP glucose, okay? And so bottom line is you want to remember glucose 6-phosphate, right, being converted into glucose 1-phosphate. Glucose 1-phosphate would most likely be in the question if they're asking you a question about glycogen. Likewise, when you get to glycogenolysis, which is the next heading, where do you think this is going to occur at again, everybody? In the liver, yes. Let's look back at that visual again. Here in this situation, obviously you're going to take glucose 1-phosphate, right, from glycogen, and you're going to convert it to glucose 6-phosphate. Okay, and then it says glucose 6-phosphate can then be converted to glucose by this enzyme glucose phosphatase. Okay, so that's kind of the big picture. When you start breaking down and building glycogen, then you're thinking about glucose 1-phosphate as part of that process. But the big thing they keep hitting over and over is all about glucose 6-phosphate. They're more likely to go into that and how it can be shuttled for pentose phosphate shunt, how it can be taken out of the cell and into the bloodstream to make glycogen, etc. So that's kind of the big picture on how you want to think about that. As we get in the next heading, which is the role of the liver, if you look at the first bullet point, it says after you eat a large meal with carbs, the liver initiates glycogenesis. You're going to store that sugar, right? But the key thing is here where it talks about during fasting conditions. So everybody look at that bullet point. It says during fasting conditions, the liver initiates glycogenolysis and gluconeogenesis. So the whole idea there again is what I mentioned earlier, is you're wanting to put glucose into the blood. Right? And it goes on to say you can spare your blood glucose, right, in fasting situations by producing ketone bodies, right? Produced from acetyl-CoA. That's what it says right there. So whenever you see a question on the test about fasting situations or low blood glucose, you want to think about ketone bodies. And as soon as you see ketone bodies, put an arrow right below that in your notes. Put brain. That's an area where they like to hit on old tests that ketone bodies can produce energy for the brain. Okay guys, so I want to point your attention to the box where it talks about how the brain almost exclusively uses blood glucose, but it can use ketone bodies if necessary. That's the phrase, again, I want you to pay attention to.